Hi, I'm Joel.
Hi, I'm Scott.
Hashtag not my TA. This is Lab 9 with Michelson interferometer applications.
Milster.
To measure the wavelength of the mercury source, we sent the mercury source through the interferometer setup, and then we aligned it so we got circular fringes. And then we moved the micrometer and cycled through 100 fringes and measured the displacement of the micrometer.
And then using the calibration from the last lab, we could figure out the wavelength. And so using the distance between the micrometer measurements and our calibration, we got 553 nanometers for our source. And plus or minus one fringe gives us an error of about 5 nanometers. And we would have to count about 5,000 fringes to get an error of 0.1 nanometers.
Milster.
To measure the wavelength of the sodium source, we sent the sodium source through our interferometry setup and counted again to 100 fringes, just like with the mercury source.
From our calculations using the calibration and the number of steps for 100 fringes, we got 593 nanometers for our wavelength of the sodium source, compared to the actual wavelength, which is 589 nanometers. This is within the range of plus or minus one fringe of counting error.
When we cycle through a large range on the micrometer, the fringe contrast washes out.
Milster.
So what I did here is I started at the 0 position of the micrometer and found 3 different null positions where the fringes completely disappeared.
So to calculate the separation of wavelengths, we cycled through 3 nulls, took the average space in between each null, and then we multiplied that times our calibration and then divided by wavelength, and we got a 0.5 nanometers of separation. The actual separation is 0.6, so it's about a 16% error. Pretty good.
Milster.
So here we're measuring how air pressure affects refractive index by changing the pressure in this little box right here. As I'm squeezing the gauge, I'm changing the pressure inside the box, which is changing the optical path difference and is affecting how our fringes collapse or expand.
We changed the pressure of the chamber until we got 20 fringes of difference. We know the wavelength of the laser and as well as the distance of the chamber, and we had to change the pressure, so from that we can find a slope.
We plotted pressure versus refractive index. Our measured refractive index for the pressure in the lab was 1.00027, which is the same as from refractiveindex.info. We used the given pressures for different altitudes to find the slope, which would give us the pressure difference between Tucson and Mount Lemmon.
We found you would need 6.6 fringes to accurately find the altitude. This would work, but you'd need very precise material, so it's not very efficient, and I wouldn't recommend it.